So far, our addLast class has these two methods. We made a sequence of these four non-obvious improvements. And we want our addList to gain even more power, more capabilities, and go off and grow up and do whatever it is that addLists do in adulthood. And to get there, what we're going to do is add two additional methods, addLast and size. Partially because we want to get a little more practice with just building data structures, but also because I want some motivation for the other two non-obvious improvements we're going to do. So what I'm going to recommend you do is try writing addLast or size on your own, maybe on paper, and then watch me do it here. So I'm going to start with addLast. And so I'm going to call this method, it's going to be public void addLast int x. And in keeping with normal Java convention, I will put it above main. And this adds an item to the end of the list. So what might this look like? Well, I'm going to write it iteratively. You could also do it recursively. I'm going to do it iteratively. And it's going to look a lot like what we did in the previous lecture. So I'm going to say int list p equals first. And then I'm going to say while p.next is not equal to null, p equals p.next. And the goal of this little chunk of code, is to scan p to the end of the list. So move p until it reaches the end of the list. And once you've done that, you can simply, you can just simply say p.next equals new int node x null. Okay, so that's addLast. We can also do l.addLast, let's say 20. And if we run this, let's see what happens. Okay, any errors? P. Oh, int node, oops. Int node. So we run this, and it runs, and the first item is 5. Now, of course, running this code, it is not clear that it worked properly. And in fact, if you look at our list of methods, there's no way that we can see what the last item even is. So we could add additional methods, but instead what I'm going to do is I am going to use our Java visualizer and see what we get. So after this code finishes running, we end up getting a layout that looks something like this. The L variable points at our middleman, which has a first variable that then points at our naked recursive data structure. And I'll make one little note. If you try running this code on your own and you end up getting a visualization that looks something like this, like a nested structure, it's just another visual representation of the same thing. If you don't want that to happen, make sure that you click Prefer Non-Nesting and Vertical Layouts. So just a quick note, if you want box and pointer diagrams, you got to click that box for our lists. So that's get back. So what about size? What might size look like? Now this one, if you didn't do addLast, if you just sat there and watched me do it, that's okay, I won't be too upset. But this one I want you to really try. I want you to really think about it. Look at the instance variables here and think, what should size look like? Try writing it out. That's my way of trying to stare you into trying it. All right. So if you try it, which hopefully you did, you'll find that trying to figure out what the base case is tricky. You'll also find that the recursive case is just equally strange. It's like, if I want to do the recursive case like we did in the previous lecture, it would seem that you want to do something like return first.next size, who knows, like some kind of recursive case, and you get a little stuck. So the issue here is that the size method, when we're writing it for addList, the addList data structure itself is not recursive. It does not have addList pointers. So the common strategy that we'll adopt, and that you'll see this time and time again as you write recursive data structures later in this course, you'll often create a private static helper method, in this case also known as size, that is going to take a particular node, and this I'm going to give a very clear comment here, returns the size of the list that starts at int node p. So here, now, this is a naked recursive data structure. This speaks the secret language of the gods, this data structure. It's just doing the usual stuff we're used to with these data structures. Let me go back to the picture and compare. So when we're working with slists, our pointers point to the middleman. We are now going to have a method that's thinking about data structures in these terms, in the naked recursive way, where we can have pointers to any place in the list. Okay. So how's that going to work? Well, now it's going to be a lot like lecture 3. I'm going to do something like this. If p.next equals null, then I can just return 1. Otherwise, we want to return 1 plus the size of p.next. So if the size method is being called on this node, for example, it'll just return 1. But if it's called on this one, we'll add 1 plus the size of this list over here. Okay? So that's what our private static method looks like. Now this is a very common pattern when working with recursive data structures, that you'll have a public method that speaks the language of mortals and a private method that speaks the language of the gods. So the public language, or sorry, the middleman, the public method, needs to use this method right here. And in this case, we'll just say the size of first. That little face I just made was me trying to get you to think. I don't know if it worked. All right. And so let's see if the size method seems to work here. Okay, indeed it does. And if you want to try it out, you can take this code that I've just written, put it through the visualizer and make sure it makes sense. But hopefully the idea is clear. So to summarize this notion, I'm sorry, to summarize addLast iteratively, not a lot of surprises, it's kind of like what we're used to. But for size, doing it recursively, we had to adopt this new programming pattern where we created a private static method that spoke the language of the gods.